Explanation with a visual representation. Why standard cells aren't near ports? Dedicated I/O cells. Specific I/O cells handle communication with the external world. These cells can handle higher voltage levels and different electrical characteristics compared to standard logic cells used within the chip's core. Physical constraints. I/O pads are typically located around the chip's periphery due to fabrication limitations. These locations provide access for bonding wires or bumps that connect the chip to external components. Standard cells reside within the central core area, away from the periphery. Potential issues with standard cells near ports. Signal integrity. Mixing high-speed I/O signals with internal logic signals can lead to noise coupling and signal integrity problems. Separating standard cells from I/O pads minimizes these issues. Routability. Routing signals between standard cells and I/O pads requires dedicated routing channels. Placing these cells away from the pads allows for more efficient routing. Visualization. Imagine the chip layout as a rectangle. I/O pads are typically placed around the edges, representing the chip boundary. Standard cells are then placed within the central core area, further away from the periphery where the I/O pads reside. Dedicated routing channels connect signals from standard cells to the I/O pads. What you might have been thinking of. Perhaps you were thinking of a different placement strategy. Clock buffers, trees. Clock signals are critical for timing. To ensure clean and consistent clock distribution throughout the chip, clock buffers or clock trees might be placed strategically within the core area, closer to groups of standard cells that share the same clock signal. However, this is not the same as placing standard cells near the I/O pads. In summary, standard cell placement aims for efficient logic operation, signal integrity, and routability. Dedicated I/O cells handle external communication and are located at the chip's periphery, while standard cells reside within the core area for optimal performance. I hope this clarifies the concept and avoids any further confusion. Feel free to ask if you have any other questions. Understanding skew and latency. Clock skew. The difference in arrival times of the same clock signal at different parts of the circuit. Ideally, all parts should receive the clock signal simultaneously for proper operation. Excessive skew can lead to timing violations and circuit malfunctions. Clock latency. The total time it takes for the clock signal to travel from its source, clock generator, to a specific register, flip-flop, in the design. Higher latency can limit the maximum operating frequency of a circuit. Importance of skew and latency in real VLSI design. Show the importance. These concepts are fundamental for analyzing timing behavior in real designs. Shows the importance. Minimizing skew ensures all parts of the circuit receive the clock signal within a tolerable time frame, and lower latency allows for faster operation. How these concepts are managed in real VLSI design. Target values and analysis. Designers set acceptable skew and latency limits based on the desired frequency and functionality. Tools called static timing analyzers, STA, estimate these values within the design and identify potential timing issues. These tools might generate reports or visualizations, like color maps, to depict the estimated variations in clock arrival times. Design refinement. The design process involves adjusting cell placement, routing, and techniques like clock tree synthesis to minimize skew and latency within the target values. My role in understanding VLSI concepts. While I can't create a specific design, I can help you understand skew and latency by explaining definitions and their impact on circuit performance, factors affecting them, circuit complexity, technology node, design techniques, strategies for managing them within acceptable limits. Importance of analysis and simulation tools for verifying timing behavior. Key points. Skew and latency are critical for timing analysis in VLSI design. I can't have these properties as I'm not a physical circuit. Understanding these concepts is a proper VLSI design. Elements are inserted to strengthen impact of insertion delay. Increased overall delay. Insertion delay adds to the overall propagation delay of the signal, potentially affecting circuit performance and timing margins. Power consumption. Additional buffers or repeaters can increase power consumption in the design. How to fix insertion delay, apart from long nets? There are several strategies to manage insertion delay, beyond simply addressing long nets. Cell sizing. Using larger sized buffers or repeaters can reduce the delay they introduce, but may also increase power and area usage. Optimizing placement and routing. Careful placement of cells and efficient routing paths can minimize the need for additional buffers, reducing insertion delay. Clock gating. Gating unused portions of the clock network can help reduce the impact of delay on inactive parts of the circuit. Logical optimization. Simplifying logic structures or using alternative logic styles can sometimes reduce the need for buffers, improving overall delay. Why? My VLSI design. doesn't apply. As a large language model, I don't create physical VLSI circuits. Insertion delay is specific to the actual design layout, cell types, and routing used. Additional tips: static timing analysis, ASTA, EDA, electronic design automation. Tools like ASTA can be used to analyze insertion delay and identify critical paths in the design. Trade-offs: managing insertion delay often involves trade-offs between performance, power consumption, and area usage. Designers need to consider these factors when making optimization decisions. Key points: insertion delay is the extra delay introduced by buffers and repeaters in a logic path. It can be managed through cell sizing, placement, routing, clock gating, and logic optimization. ASTA tools help analyze insertion